All right. Good afternoon. Just picking up once again with intervals and looking at solving for for inequalities. And again, we have in the case of continuing with what we have for rational inequalities. And let me kind of give you a bit of a foundation. Okay, and I had left off. Okay, saying looking at solving the comparison to zero inequalities with a rational function, okay, whereupon we have r of x is equal to, okay, so we have x squared plus 5x plus 4, and we have all over x squared minus 2x minus 3. Okay, now we're kind of going to go back just a few sections. Again, just kind of looking at what we had when we were looking at the domain of a rational function. And again, for the domain of this one, okay, again, for a fraction, the denominator cannot be equal to 0. Okay, so in terms of the domain, okay, so if x squared minus 2x minus 3 cannot be equal to 0, okay, then the factors of the expression cannot be 0 either. So we have, with the factors, okay, so we have x minus 3 and x plus 1. So we have, in the case of x minus 3, okay, x cannot be equal to 3. And as for x plus 1, okay, again we have x plus 1 cannot be 0. And so we have that x cannot be negative 1. Okay. And now for the domain, again we have at the lowest end. Okay, so we have okay, between 3 and negative 1. Negative 1 is the smaller of the restricted values. Okay, so the domain, we have those values, okay, less than negative 1. Then we have those values, x greater than negative 1 and less than 3. And then we have those values of x that will be greater than 3 at the upper end. And just going back to asymptotes. Okay, now if we're looking for vertical asymptotes, again we have r of x. Again we have x squared plus 5x plus 4. All over x squared minus 2x minus 3. And again, you look for the exclusions from the domain before any reduction is performed. And looking at factoring what we have in both the numerator and denominator. So we have with x squared plus 5x plus 4. Okay, so we have among the factors, okay, we have x plus 1 and x plus 4. And again, we have with factoring x squared minus 2x minus 3. So again, we have the quantity of x minus 3. And we have times the quantity of x plus 1. And for what's going to happen here, okay, we're going to have x plus 1 to completely cancel. And so the reduced form for this rational function is going to be x plus 4 all over x minus 3. So again, we have x plus 1 completely cancels. And if the denominator factor completely cancels, that means that for the restricted value, there's going to be a whole. Okay, so we have a whole, in this case, at x is equal to negative 1. Now for the reduced form, again, x minus 3 remains. So the corresponding 0, which is the restricted value 3, that is going to be the vertical asymptote. Okay, so you have a vertical asymptote at x is equal to 3, and again, you have a hole at x is equal to -1. Now, in terms of any other asymptote, okay, so this comes down to degree comparisons. Okay, so we have, for the numerator, again, we have that n is equal to 2. And in the denominator, okay, we have that m is equal to 2. Okay, and again, in terms of how the degrees compare, n is at 2, m is at 2, so the values are going to be the same. And again, if n is less than m, or if n is equal to m, we're going to end up with a horizontal asymptote. And for what we have here, for the horizontal asymptote, okay, we have y is equal to a constant that will result from taking the ratio of the highest degree terms from the numerator and denominator. And we have these to be identical. So you have x squared from the numerator, x squared is the highest degree term in the denominator, and x squared over x squared, okay, reduces to 1. Okay, so for what we have in the overall picture, okay, so we have in the development so far, okay, we have the rational function. Okay, you have r of x. Again, you have those curves in blue. So you have x squared plus 5x plus 4 over x squared minus 2x minus 3. And again, we have with the asymptotes, again, there's a vertical asymptote, which we have at x is equal to 3. And we have a horizontal asymptote at y is equal to 1. And again, just restate, okay, we have a hole at x is equal to -1. Okay, so just again, at this location, okay, and again, this is just illustration of what we have for this rational function along with the asymptotes. And again, the rational function does have a hole situated at x is equal to -1. Now, in terms of what we have in context regarding comparison to 0 inequalities, so we're working with the rational function. And in a sense, we're going to be looking at hitting the reset button, but I'm going to bring it all back together. Okay, so we have for r of x, again, we have x squared plus 5x plus 4. Again, we have all over x squared minus 2x minus 3. Okay. Now, in terms of the zeros of r of x, okay, for what I'm going to have in this particular case, I'm going to be taking zeros of both the numerator and denominator. Okay, so we have just for this expression, so just to restate, okay, so you have with the factored form. Okay, so I have the quantity of x plus 4 times that of x plus 1. And again, we have all over the quantity of x plus 1 times that of x minus 3. Okay, so we have, just for starters, okay, looking for the zeros. Okay, so you had the factored forms. Okay, so we have x plus 4. Okay, that's equal to 0. And from this, we have that x is equal to negative 4. Okay, so in this particular case, all right, so negative 4 stems from x plus 4, which is exclusively in the numerator. And you can have a zero-valued numerator as long as you do not end up with also a zero-valued denominator. So x equals negative 4. Okay, now this one is in the domain. Because the factor is only in the top part of the fraction. Okay. Now for the other variable factors, okay, so we got x plus 1 is equal to 0, and we have that x is equal to negative 1. Now, because x plus 1 is in the numerator, it can be very easy to assume that negative 1 is in the domain. However, since x plus 1 also appears in the denominator, guess what? While we can have a 0 numerator, again, you cannot have also a 0 denominator. And this is exactly what would happen with x equal to negative 1. You would have, along with a 0 numerator, you're going to end up with a 0 denominator. So the overriding, I guess you say, tiebreaker in terms of whether negative 1 is in the domain or not is going to be with the denominator. So in this case, right, negative 1 is not in the domain. And for what we have in the case of x minus 3, again we have x is equal to 3, and because this stems from the denominator factor x minus 3, again if we have x at 3, the denominator also ends up at 0. So 3 is going to be also excluded from the domain. All right, so just so for just the readdressing of what is in the domain and what is not, again, we had for this function, once again, when we were looking for the domain, only 3 and negative 1 were restricted. And this is from a different angle, but this is just saying once again that 3 and negative 1 are not restricted, but not in the domain, and negative 4, again, not restricted, so that is in the domain. Now, so we have, again, just compositing together. Okay, so we have our function, r of x, equal to x squared minus 2x minus 3. And we have, once again, just for the zeros, again, we have negative 4. I'm going to do a little bit of color coding and abbreviating. Okay, so negative 4 is ITD, like in the domain. And you have negative 1. Not in the domain. Also have 3. Also not in the domain. Okay, but now with these 3 zeros, we're going to set up a table of intervals, okay, that will be centered about these zeros, regardless of whether you have them to be in the domain or not. And so for what we have, once again, in setting up the table of intervals, okay, so you have these 3 zeros involved. Okay, and it turns out that we do have these in increasing order. So we have negative 4 is the smallest of these, so we can have a set of values x that will be less than negative 4. And then we'll have those values of x greater than negative 4 and less than negative 1. And we have those values x, okay, greater than negative 1 and less than 3. And then we have those values x, okay, which will be greater than 3. Okay, and so just again, forming a table about these zeros and the intervals that originate from them. Okay, so I have for the sections. Okay, so look at partitioning. Okay, and again, so we have for the inputs. Okay, say we have in the case of the tested value for anything that is less than negative 4, okay, something like negative 5 would fit the bill. And for anything between negative 4 and negative 1, if you were to select integers, you go with either negative 3 or negative 2. Again, anything between negative 1 and 3, but not including negative 1 or 3, you can select 0, 1, or 2, okay, if you continue to maintain the use of integers. And then anything greater than 3, okay, we can just go with the number 4. Now for what we have in the case of the value of r of x, again we have x squared plus 5x plus 4 all over x squared minus 2x minus 3. Okay, so we have with our values, okay, and the output. Okay, so you have r of negative 5, r of negative 2. You have r of 0 and r of 4. And we'll go ahead and tackle r of 0. So if I have 0 for x, okay, so you have 0 plus 4, so you got positive 4 at the top, and what will be negative 3 at the bottom. So here, r of 0 will be at negative 4/3. Now for r of negative 5, okay, so in the development, okay, so we're going to have the square of negative 5, and I have plus 5 times negative 5. Yeah, plus 4. And here we have 5 squared. Make that negative 5 squared. We have minus 2 times negative 5. Minus 3. Okay, so you got negative 5 squared. Okay, so you have 25. Minus 25 plus 4. Negative 5 squared again is going to be 25. And you got plus 10 minus 3. Okay, and what's going to happen here? So you got 4 over 32. And so that is going to reduce to a positive 1/8. Yes, that positive 1/8. Okay, now for r of negative 2. For r of negative 2, okay, so we have negative 2 squared. Then we've got plus 5 times negative 2 plus 4. And we have negative 2 squared minus 2 times negative 2 minus 3. Okay, so just taking what we have here. So we have negative 2 squared is 4. 5 times negative 2 is negative 10. And we have plus 4. Negative 2 squared again is 4. Negative 2 times negative 2 is positive 4. And we have minus 3. So we got what's going to be negative 2. 4 plus 4 is 8. Minus 3 is going to be 5. Okay, so right away we're going to have negative 2/5. Now for what we have in the case of R of 4, okay, so for x squared, so we have 4 squared plus 5 times 4 plus 4. And here we have 4 squared minus 2 times 4 minus 3. Okay, so 4 squared is 16. 5 times 4 is 20. Yeah, plus 4. 4 squared is 16. Negative 2 times 4 is negative 8. And we have minus 3. So for what this would come down to, so you got 36 plus 4 is 40. And 16 minus 8 is 8. Minus 3 is 5. So 40 over 5, you have a positive ratio. So this will reduce to positive 8. Okay, and just looking at what we have for the sine value. Of R of x. Okay, so for the sine of R of x, so anything we select for the input that is less than negative 4, we're going to have a positive output. So in this case, R of x will be greater than 0. Anything we select between negative 4 and negative 1, the output is negative. Okay, so we have the R of x is going to be less than 0. Okay. And then we have for what we have next, anything between negative 1 and 3. You also have a negative output. So R of x is less than 0. And then for the last section, okay, we'll have a positive output. So we have the R of x is greater than 0. Okay. Now, just looking at what we have in the setup. And if I take each of the inequalities. Okay, first of all, if I have x squared plus 5x plus 4. Okay, we have all over x squared minus 2x minus 3. Okay, say if this is less than 0. If this is less than 0. So this will be referencing what we have for R of x is less than 0. Okay. So where we have less than 0, so you have, again, there's no equal sign, so we're going to have the exclusive use of parentheses. Okay, now, in the case where we have the rational expression to be less than or equal to 0, Okay, so you have less than or equal to 0. Okay, so it'll be in the same direction as where r of x is less than 0. So I'm still involving the limit values, -4 and -1, as well as -1 and 3. And just kind of taking what we have here, just doing a little bit of color coding. Okay, now with an equal sign, there is the potential for there to be brackets, but it's not necessarily a guarantee. So for -4, okay, -4 is a 0, and it will be bracketed as long as -4 is in the domain. So looking back, -4, again, this stems from x plus 4, which is only in the numerator. So this is in the domain. So around -4 is going to be a bracket. However, with -1 and 3, again, -1 and 3 have their respective factors to be included in the denominator. So there's no way that these can be in the domain. So we have parentheses around those particular values. Again, you have an equal sign, but that doesn't guarantee you're going to have unanimously the use of brackets among the finite values. Okay, because -1 and 3 are not in the domain, only -4 is. Now, and looking at what we have with the change in direction. Okay, so I have x squared plus 5x plus 4 over x squared minus 2x minus 3 is greater than 0. Okay, so looking at where we have r of x to be greater than 0, no equal sign, so we're going to have just the use of parentheses. So we have those values of x less than -4 at the front, and then we have at the end. We have the other step, which would be those values of x which would be greater than 3. And then for what we have in the case of where we have the rational expression to be greater than or equal to 0. And again, just a bit of history repeating. Okay, so again, just to kind of stress, okay, so again, 3 is not in the domain, whereas -4 again is the only 0 that is in the domain. So in terms of the grouping, okay, so you have values of x. Okay, so you have around -4, and -4 is included since -4 sets the function equal to 0, whereas in the case of 3, it's a 0, but it's the kind that will render the expression as undefined. Okay, so those will be your respective interval solutions for the inequalities from less than 0 to greater than or equal to 0. And again, for there to be any bracket, it'll be where we have the inequalities with the equal sign and where the corresponding finite value is in the domain, and -4 being only that particular value. Okay, and I just wanted to kind of reference the graph for just a moment, and I'll just situate this underneath the table here and the inequalities. And I was going to mention now it's the same graph, but I just included some details. Now I still had the rational function, that blue curve, that is separated by the asymptotes. X is equal to 3 and y is equal to 1. And again, for what we have among the values. Now, when we looked at applying the test values, they have like -5, and the output was 1/8. Well, guess what? Over here we have -5, 1/8. And when x is -2, the corresponding rational expression value was at -2/5, so that's -0.4. And with x at 0, you got -4/3 or -1 1/3. And then we have with x at 4, the rational expression, again we have equal to 8. And just what I'll do here is I will enlarge the view. So again, you still have the same graph, the same asymptotes, and just applying points like -5 1/8, -2 2/5, 0 -4/3, and you still had that whole at x is equal to -1. And again, we have when x is 4, your corresponding rational expression value is going to be at 8. So any supplied points with the test values, they will still be in compliance with all the other details like the graphing, the asymptotes, what is in the domain, what is excluded from the domain, all those items. I know it's one big micromanaging package and all that, but it all does flow together. All right, and now for what we have now, and looking at sort of tying in together what we have with rational inequalities, and there's going to be an item, okay, that'll be referred to as comparison inequalities. And I'll give you some cases, and it's not going to be the level of granular breakdown. Let's say that in the case of comparison inequalities, okay, so you have for comparison inequalities. And we'll say that we have, let's say if you have a rational expression. And we'll just keep it basic. I like to keep it basic where I can. Let's say we have r of x is equal to 1/2x. Okay. And now, just for the zeros, guess what? There's only one variable expression, and that's going to be in the denominator. So 2x is equal to 0, and from this x is equal to 0, and since this stems from the denominator, okay, so this is not in the domain, and so just kind of repeating. Okay, so you have r of x is equal to 1/2x. And again, we have with the only zeros. So you have 0. And again, we have NITD, not in the domain. And so if I were to set up a table of intervals, and this will be a narrower table since I only have 1 0 involved. So you have with the two extremes, you have like those values x that will be less than 0, and then you'll have those values of x which will be greater than 0. Okay, and just for the test values. Okay, for the test value x, so anything less than 0, okay, we'll just have, we'll say we have -1, and then anything greater than 0 will be a positive value. We'll just go with the number 2. Again, we have r of x is equal to 1 over 2x. And for r of -1, okay, we have 1 over 2 times -1. And we have 1 over -2, so this is going to go to -1/2. And for what we have in the case of r of 2, so we have 1 over 2x becomes transformed to 1 over 2 times 2. And so this will come out to 1/4, which will be a positive number. Okay, and for the sign of the rational function, okay, so for any negative values, the output is going to be negative. Anything greater than 0 for the input, the output is going to be positive. Okay, so we have r of x is greater than 0. All right, so just working with our possible inequality scenarios. So for 1 over 2x is less than 0, so you have r of x is less than 0. Okay, so no equal sign, so you have automatically only parentheses will be used for grouping symbols. And if I had that 1 over 2x, is less than or equal to 0. Okay, now again you have going in the same direction as r of x is less than 0. So you're still looking at negative infinity. Infinities are boundless, so negative infinity stays in the parenthesis. But now for 0, there's the temptation to put a bracket around 0. But guess what? 0 is not in the domain. So that's going to stay in the parentheses. I'm going to put the red like referencing not in the domain. Now for 1 over 2x is greater than 0. Okay, so when x is positive, okay, we have the rational expression is positive. So and then for 1 over 2x is greater than or equal to 0. So again, you have the same direction as r of x is greater than 0. So you're still involving 0 and infinity. Again, infinity is boundless. And now with the equal sign, again, there is the potential, but not the guarantee that there will be a bracket. And guess what? 0 is our only finite value that we're working with. But guess what? That creates a 0 denominator situation. So that is not in the domain. So guess what? We have parentheses only. So the less than or equal to solution is the same as what was for less than. And the greater than or equal to identical to what was for greater than 0, and the reason being that there was no 0 from this rational expression in the domain for this particular item. So those are the fruits thereof of what we have for a rational function r of x. Now let's say that just a little bit of a crossover, and tell you what, just sort of tying in together. Okay. Let's see what we get for these inequality solutions, and we'll say that we have for r of x is equal to, and we'll say we have x minus 4, and we'll say we have all over x plus 2. Okay, so for the next few moments, let's see what inequality solutions we get for these comparison to 0 inequalities for the function r of x is equal to x minus 4 all over x plus 2. Okay, just in the case of what we have as comparison to 0 inequalities, now we have assigned, okay, the rational function r of x is equal to x minus 4 all over x plus 2 and again, if we identify the zeros, okay, so you have from the numerator, if x minus 4 is equal to 0, we have that x is equal to 4. And again, because this factor or this expression is in the numerator, okay, that one is in the domain. And as for x plus 2, our other variable expression, now this one is in the denominator. So any 0 from this, in this case, which will be negative 2, okay, that one is not in the domain. All right, so just kind of compositing together in the setup, or for the setup in our table. So we have r of x, we have equal to x minus 4 all over x plus 2. And again, we have for the zeros, again we have 4, again, which you have, again, is going to be in the domain. And again, because negative 2 stems from x plus 2, which was in the denominator. Okay, again, that value is not in the domain. Okay, and so just looking at our zeros. Okay, so if we set up a table of intervals, okay, and again, so we have starting from negative infinity, approaching the smaller of the exclusions, or I should say smaller of the zeros. Okay, so we have negative 2 being the smaller, so those values of x less than negative 2. you have those values of x greater than -2 and less than 4. And then we have those values of x which will be greater than 4. And again, if we look at supplying test values, okay, so for anything that is less than -2, okay, we can just go with -3. Anything between -2 and 4, okay, 0 will fit the bill. And anything greater than 4, we'll go with the number 5. Okay, and I'll just go ahead and set up the table formation. Okay, so applying each of these test values, okay, for the rational function. Okay, so we have with r of -3. Okay, so we're going to have, in essence, okay, so you're going to have r of -3. Now, -3 minus 4, this will be a -7. -3 plus 2 is -1. And guess what? This will reduce to a +7. In the case of r of 0, okay, we have 0 minus 4 over 0 plus 2. So it'll be -4 over 2. So that reduces to -2. Now, so what we have in the case of r of 5, okay, you have 5 minus 4 is 1, 5 plus 2 is 7. So right away, this will become positive 1/7. And for what we have in the case of the sine of r of x, okay, so looking at the respective outputs, okay, we have +7 from the sample. Okay, so anything plugged in less than -2, the output is positive. So we have the r of x is greater than 0. Anything from the second subinterval, then we have a negative output. So you have r of x is less than 0. Anything from the last, okay, we're going to have a positive output. Okay, so we're going to have the r of x, okay, is greater than 0. Okay, so for what we have among the inequalities, okay, and we have here, okay, now listen, my MacBook Pro needs charging, so sorry about that. Okay, so we got with a rational expression. So we have with r of x, okay, x minus 4 over x plus 2. So where r of x is less than 0, okay, we already have in play where r of x is less than 0, and you have the solution will be those values x greater than -2 and less than 4. Now where we have x minus 4 over x plus 2 to be less than or equal to 0. Again, you're still in the same direction. as less than 0. So you're somehow involving negative 2 and 4. Now 4 is in the domain, negative 2 is not. So negative 2 is going to stay in the parentheses, whereas 4, since that officially sets the rational expression equal to 0, we're now going to have this in the bracket. And for what we have regarding r of x being greater than 0, so we are involving the first and the last subinterval sections. And again, no equal sign, so we have the exclusive use of parentheses. So those values of x less than negative 2 and those values of x greater than 4. And we have for r of x is greater than or equal to 0. Okay, so again, we're still looking at working around negative infinity, negative 2, as well as 4 and infinity. Since again, the inequality is in the same direction as greater than. Okay, so again, infinities are boundless. So we still maintain the use of parentheses. And again, for negative 2 and 4, okay, where the we might have the inequality equal to 0, or I should say the rational expression equal to 0. So negative 2, again, this is not in the domain. So this stays in the parentheses, and only 4 can set this function officially equal to 0, and 4 is in the domain. And again, this value is going to be in the bracket. So those will be your respective interval solutions. And again, for there to be a bracket, you must have an equal sign, and the zeros involved for them to be bracketed must be in the domain, and 4 being such that number. All right, now there is an item, and I'm going to touch a bit lightly upon this. And I think the caliber of the problems in Alex might be somewhat, I'm trying to think of a better term, maybe a little bit higher, a little bit more painstaking, I guess you can say, in comparison to some of the book problems. And I'll give you a case of comparison inequality, and where we don't have a comparison to 0, but instead a comparison between rational expressions. And let me give you just a case, and I'm going to give you a bit of a backdrop. Let's say if you have comparison inequality between rational expressions. Okay, let's say we have 2 over x plus 2 is greater than or equal to 1 over x plus 4. And of course, we're solving for x. Okay, so we have 2 over x plus 2 is greater than or equal to 1 over x plus 4. Now, if I rewrite what I have here as a comparison to 0 inequality, so 2 over x plus 2, and we have minus 1 over x plus 4. So if I move the fraction on the right over by subtracting, so we have 2 over x plus 2 minus 1 over x plus 4 is greater than or equal to 0. Now, before I start taking the zeros, if I have a sum or difference between fractions and they don't have the same denominator, I'm going to combine these, cluster them together in terms of the least common denominator. Okay, so just kind of stepping to the side here. So if I have 2 over x plus 2 minus 1 over x plus 4, Okay, so I'm looking at combining the fractions. And so we're going to have for the least common denominator. Okay, that's going to be the product of x plus 2 and x plus 4. Okay. So for this difference, if I write as a consolidated ratio, so I'm going to have 2 over x plus 2. Now for the least common denominator, okay, I have the x plus 2 factor. However, this ratio is missing the x plus 4. So I'm going to multiply by 1 in the form of the missing factor, in this case, x plus 4 divided by itself. Again, we have subtraction. Now we have 1 over x plus 4. Now we have the x plus 4 factor, but missing will be the x plus 2. So this ratio will be multiplied by 1 in the form of x plus 2 over itself. Okay, so we have for the first part, okay, so I have 2 over x plus 4. And I can go ahead and distribute. So I have 2 times the quantity of x plus 4. So this will be 2x plus 8. I have all over x plus 2 times x plus 4. Now I have subtraction in between. And I got 1 times x plus 2. So this will be x plus 2. And I'm going to have the same denominator. Okay, so I have still separated, okay, by the operation of subtraction. Now once I look at consolidating, okay, so the denominator, okay, you have x plus 2 times x plus 4, or x plus 4 times x plus 2. Okay, so you got 2x plus 8. Now for the second ratio, the numerator was x plus 2, but both of these terms will be affected by the subtraction right in front of it. So as we look at gathering, so I have 2x plus 8. And what was x plus 2? Both of these terms will be negative, for they will be affected by the subtraction. So you have a minus x and a minus 2. And looking at what we have in the numerator. So you got 2x minus x is going to be x. 8 minus 2 is 6. Okay, so as a consolidated ratio, notice I have not 2 variable expressions as before, but upon consolidating, I end up with 3. So again, just consolidating. And it's going to turn out that for the completed expression, okay, so I'm going to have x plus 6. All over the quantity of x plus 2 times that of x plus 4 is greater than or equal to 0. So this is our way of saying that we're converting this comparison between ratios inequality to what we have with writing in terms of a consolidated rational expression, in this case greater than or equal to 0. Okay, and I'm just going to mention now for the setup from the comparison inequality. Okay, so we have for r of x, okay, so we have x plus 6 and we have all over the quantity of x plus 2 times that of x plus 4. Okay, now for the zeros. Okay, now for x plus 6, this is exclusively in the numerator. So the 0 from this is negative 6. So you can say negative 6 is in the domain. Now for x plus 2 and x plus 4, okay, those factors are in the denominator. So if x plus 2 is equal to 0, we have x equal to negative 2. Okay, but again, negative 2 is not in the domain. And for x plus 4 is equal to 0, now x plus 4 is in the denominator, just like x plus 2. So the resulting 0 from this, which we have at negative 4, okay, you also have not in the domain. Okay, so if we look at setting up a table of intervals, okay, and again, we have revolved about these zeros. So you have for the first interval, so you have going from negative infinity to negative 6, but not including negative 6. Then we have bypassing negative 6 and approaching but not including negative 4. Then we have bypassing negative 4 and approaching but not including negative 2. And again, we have with negative 2 is the highest of the zeros. Okay, the rest of the intervals, okay, we have at the upper end, you have those values of x greater than negative 2. Okay, so we have our separate intervals, and again, so looking at applying test values. Okay, so anything less than negative 6, we can just go with negative 7. And between negative 6 and negative 4, if we still maintain the use of integers, we can only apply negative 5. And similar kind of circumstance we have between negative 4 and negative 2. If we stick with integers, we got negative 3. And then anything greater than negative 2, you can say negative 1 or the ever so popular 0. Okay. Now, so just looking at what we have for the function values. Now, still we have r of x is equal to x plus 6. We have all over x plus 2 times the quantity of x plus 4. Okay. And just looking at what we have for each of the inputs. Okay, what I'm going to do, I'm just going to go ahead and just put down the outputs. Okay, so we have like R of 0. Okay, so you have 0 plus 6 is 6. You got 0 plus 2 is 2, 0 plus 4 is 4, 2 times 4 is 8, and 6/8, okay, that is going to be reducible to a positive 3/4. Okay, now for R of negative 7. Okay, now for this one, now you're going to have negative 7 plus 6 is negative 1, and then you have with the denominator. Okay, we have like negative 5 times negative 3, and so in this particular case, all right, we're going to have negative 1 over 15, so this will be a minus 1/15. Okay, now for what we have in the case of R of negative 5, okay, so this one is going to end up reducing to a positive ratio, and I'll go ahead and put this one down. So this is going to be a positive 1/3. And in the case of R of negative 3, okay, this is just going to reduce to a negative value, and in this case, this is going to be a minus 3. Okay, so in the case of the sign of R of x, so anything I plug in less than negative 6, the output is going to be negative. So we have the R of x is less than 0. And then we have anything greater than negative 6 and less than negative 4. Okay, again, the output is going to be positive. So we have R of x is greater than 0, and then we have next, we have a negative output, so we have R of x is less than 0. And then for the last case, we have a positive output. So we have the R of x is greater than 0. Okay, so just kind of going back to what we have with the original problem. Okay, and so we start out with 2 over x plus 2 is greater than or equal to 1 over x plus 4. And then I converted as a comparison to 0 inequality. And again, I combine these expressions into 1 after the process. And the consolidated ratio, again, we have x plus 6 all over the quantity of x plus 2 times that of x plus 4 is greater than or equal to 0. And now, in the case of what we have with the solution, okay, where we have R of x is greater than or equal to 0. Okay, so you have the same direction as where R of x is greater than 0. So we're looking at applying the limit values. Negative 6 and negative 4. And where R of x is greater than 0, so you have between negative 2 and infinity. And again, we got the equal sign, so there could be brackets in the midst. Okay, now for enclosing, now infinities are balanced, so infinity stays in the parentheses. Now for negative 6, negative 4, and negative 2, Okay, again, so you have whether items, now -6 is in the domain. -6 is in the domain. This does create the equal to 0 part. So -6 is going to be in the bracket. So that value sets the function equal to 0. Whereas with -4 and -2, since those are not in the domain, what happens is that because their factors are in the denominator, instead of equaling 0, we have instead creating a situation where the rational expression winds up becoming undefined. Okay, so we have, so for the completion, in this one case, you have -4 is going to be in the parenthesis, and so will -2. So this will be the outcome in this one.